Hello, welcome to the second part of the video on ultraviolet catastrophe and black body radiation. In the previous video, we talked about what a black body is and how it functions. In this video, we'll see a complete mathematical derivation of the Rayleigh-Jeans Law, which ultimately led to the ultraviolet catastrophe and then to the birth of quantum mechanics. Now, this video will have 4 subsections. Part 1 will be a revision on waves in a box. So we will consider the properties of waves in a box and then consider the electromagnetic modes in a box and eventually work out how what is the energy of each mode in thermal equilibrium at say temperature T. Then in part 3 we'll find how many modes are there distributed in a frequency bandwidth of or frequency difference of d mu. Then eventually we'll take an average across all frequencies and ultimately find that something went wrong with classical physics. Right? So without wasting any time, let's start with part 1. So when we talk about waves in a box or any wave in general, waves are represented by the equation. Say you have a wave traveling in direction r, then it's a sinusoidal wave. This will be its form. So this is its amplitude a, right? And this will be its wavelength lambda. Let's call this a naught. Now a as a function of r will be a naught sine of, say this is 2 pi r by lambda, where lambda is the wavelength, and we know that if lambda is the wavelength and if mu is the frequency, then lambda into mu is c. Since it's an electromagnetic wave and we are mostly talking about vacuum, lambda into mu will be c, where c is the speed of light in vacuum. Let's denote this constant 2. Let's denote 2 pi by lambda as k, right? And if the wave evolves with time, as in say the wave propagates towards plus r in time, then we might have the equation as follows: a naught sine 2 pi r by lambda minus 2 pi by lambda into c into t. Right? Now 2 pi by lambda is k, which I have made the substitution there. So it's a naught sine kr minus kct. Now kct you can further simplify. Now k is 2 pi by lambda and c is nothing but lambda by mu. So k into c will give us lambda cancel, 2 pi by mu, 2 pi by mu, and c is lambda into mu, so 2 pi mu, and this is equal to omega, the angular frequency, right? So as a function of r will be a naught sine kr minus omega t. Now this is the equation of an electromagnetic wave traveling along vector r with in time t. K is called the wave vector. It's essentially k bar dot r bar, where r is your radial vector and k bar is called your wave vector. Now next, let's see part 2, that is electromagnetic modes in a box. Now what do we mean by modes is quite simple concept. Consider a cubical box, say of length L. This is the length of the box, length L. And imagine that the waves is bouncing back and forth inside it. The box has fixed, rigid, perfectly conducting walls. Now, therefore, the electric field of the electromagnetic wave must be zero at the walls. If it were positive, there will be some attenuation or loss of energy at the walls. And this kind of becomes our boundary conditions. So we can only fit waves into the box which are multiples of, say if a wave can only be as follows or as follows, where its amplitude becomes zero at the walls. Now this is the condition where, look, this is half a wavelength, right? And this becomes one full wavelength as this. So this is one full wavelength and this is half a wavelength. Similarly, a wave can be like this or like this, and we have perfect rigid conducting walls, right? In the first case, we have lambda by 2 is equal to L. In the second case, we have wavelength equals L. The next thing we can have is something like this. So first we had this, then we had this. Now next we can have this as well. Here this is lambda and this is lambda by 2. Lambda and this is lambda by 2. So this adds up to 3 lambda by 2 equals L. Similarly, if we keep going on, you find the general trend that n lambda by 2 equals L, or lambda equals 2L by n. You find that for no loss of energy, for the wave to continuously move back and forth, its wavelength is quantized. Wavelength can only be 2L by n, where n is an integer, right? Now this n is just a positive number, right? Now here we only talked about x-axis. Now when you talk about a three-dimensional box, you have your x-axis, you have your y-axis and your z-axis, right? So now you have similarly, like x, you have 2 lambda is equal to L by n. For y and z, you might have that lambda equals 2L by m and lambda equals 2L by k for y-axis and along the z-axis, right? Now let's see if this imposes a condition, a criterion on our wave function, right? So the wave function we saw earlier was a as a function of r will be a0 sine of kr minus omega t, right? Now at say time equals 0 and r is equal to 0, so that is if we have a wave form like this at t is equal to 0 and at r is equal to 0, the wave function is equal to 0. And the only possible way sine function is 0 when it is n pi, right? So if you continue doing the calculation so since we can say x, we consider only in the x direction, not r, we have if kx will be equal to 2 pi by lambda x, where kx is the component of the wave vector of the mode of oscillation in the x direction. Hence the values of kx which fit into the box are those for which lambda x is equal to 2L by a natural number. So you have kx is equal to 2 pi L by 2L, where L is a natural number. This becomes pi L by L, where L takes on the values 1, 2, 3, blah, blah, blah. And similar results can be found for y and z axis, where you have ky equals pi m by L and kz is equal to pi n by L, where again m and L can take on the values 1, 2, 3, 4, 5, blah, 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 blah. So these, when you talk about the values of kx, ky and kz, they form a regular cubical array of points, right? I can have L, M and say N, a three-dimensional set of points everywhere, three-dimensional set of points that form a regular cubical array of points, each of them defined by 3 integers, right? It's like a vector in 3 dimensions. Now the waves we are considering can oscillate in all 3 dimensions, but the components of their k vectors or wave vectors kx, ky and kz must be such that they're associated with one of the points in the lattice here, right? A wave oscillating in 3 dimensions with any of the allowed values L, M, and N satisfies the boundary conditions which we have already talked about, and so every point in the lattice represents a possible mode of oscillation of the waves. I hope that makes sense. Now, if the waves are within the box, the boundary conditions should be met, and kx, ky, kz must be, can have any set of values that these things are clarified. One important thing we can do is we need to see if this gives us something new with the equation of a wave. Assuming that everybody knows, so the equation of a wave is this. So you have 1 by c squared dou squared by dou t squared phi. Now, if phi is any function of time, t, and space, then phi can be a wave equation if this is the Laplacian of phi and 1 by c squared is the wave velocity in this. So if I consider my phi to be a sine kr minus omega t, and if I perform these the Laplacian and the partial derivative with respect to time twice, then this condition must be satisfied. Now, when we considered this as an initial wave, we only thought about the x direction, right? Now, for our wave in 3 dimensions, the modes of oscillation are independent. Each particle can oscillate in any direction, and the only constraint is on its wave vectors. So you can write something like this. A as a function of x, y, and z can be written as a0 sine kx into x, sine ky into y, and sine kz into z. Now, to find the relation between kx, ky, and kz and the angular frequency omega of the mode, that is this, we insert this equation into the general wave equations in 3 dimensions. Now, I'll leave it as an exercise. If I find the second derivative of this with respect to x, now I'd like to remind that if you have del squared, this is nothing but dou by dou x squared plus dou by dou y squared plus dou by dou z squared in Cartesian coordinates, right? Now, if I perform the operation of del squared on this equation, that would just, I'm just eyeballing it, would be this dou by dou y squared dou z squared. This will be equal to 1 by c squared dou squared a by dou t squared. Now this will, the second derivative of a with respect to x, with respect to y, with respect to z, will all give me my kx, ky, kz vectors. Try that as an exercise. So you will get that kx squared plus ky squared plus kz squared equals 1 by c squared into omega squared. Now this can be written as mod k squared is equal to omega squared by c squared, where mod k is the 3-dimensional wave vector, right? Now we've arrived at a good conclusion. Let's have a look at that. What we can do now is capital K squared, try to manipulate RHS here, kx squared, ky squared plus kz squared will be equal to, now omega can be written in terms of L and M. Instead of that, since I already have the relations for k, I can use them, right? So k is nothing but kx is pi L by capital L, k is pi M by capital L. This will be pi squared by L squared plus M squared plus N squared, right? And omega can be written as pi squared by L squared into P squared. Simple. Omega squared by C squared. So this, equating both of these, gives me the wonderful relation L squared plus M squared plus N squared is equal to P squared. And we have finally arrived at a wonderful conclusion if you look at the values of L, M and N and P, let's say I'll plot a graph like this. I have L, M and N. If I give you a value of L, M and N, then the set of points P will be the sphere formed by N and M. This is basically the equation of a circle in 3 dimensions, and P is the set of points on the surface of the circle, right? If I give you points L, M and N, then the value P will be the surface of the circle. So we have this beautiful relation, and now we move on to part 3, which is all about counting the number of modes, that is L, M and N, in a given frequency range, right? Part 3. Now, we need the number of modes of oscillation in the frequency interval of mu, mu plus d mu. We're trying to find number of modes in this frequency interval, right? This is now straightforward actually, but since we already know that in the L, M and N space, how in the space of L, M and N, we can directly find P, this turns out to be not a very difficult exercise, right? Now in this figure, you can see the number density of the lattice points per unit volume. If you consider 1 unit volume of this area, take it out and have a look at this. Have a look at this points. We only want the number density per unit volume, that is the number of modes possible in this volume of area, right? Here you have DL, you have DM, and out of the plane coming up towards the camera you have DN, right? We're only now one more thing, one constraint we have is we're only interested in the positive values of L, M and N, right? We don't want negative L, M and N, and that reduces our sphere area by 1/8, right? Half because we're considering the positive upper half, half here, half along the X, half along the Y and half along the Z. So the volume of our sphere is 1/8. Now the number of modes I want in this differential volume, write it as dN, as a function of P, will be the number of modes in number of modes in a difference dP and into dP. This is 1/8 times 1/8 is the entire volume. I have reduced it already. Now the volume of a spherical shell, if you consider a spherical shell of radius P and thickness dP, that is this. If you have a shell as follows with radius P and thickness dP, the volume is given by 4 pi P squared dP. 4 pi squared is the area of this surface. You multiply the area into the thickness and you get the volume of the sphere, right? So the volume of the spherical sphere of thickness P and dP, of radius P and thickness dP, is 4 pi P squared dP. So the number of modes dN found in the octant is given by, let me write this down, 1/8, because we are reducing the octant size by 8, into 4 pi P squared dP. Now we can use this relation where you can say that K was equal to pi P by L from the previous slide. Pi P by L, differentiate both sides, you get dK is equal to pi dP by L. Now we find dN as a function of P to be L cubed by 2 pi squared K squared dK. I'm just substituting the value of dK in this equation. So we have the number of modes of momentum P with a wave vector element dK. Now we can do a couple of substitutions here. Note that L cubed is the volume and I can represent that by V. It is the volume of the box. And K in other terms can be represented as 2 pi mu by C. Right? where mu is the frequency and c is the velocity of light. So we can write the following expression for the number of modes of with momentum difference p plus d plus p to p plus dp. P plus dp as follows: b k squared dk squared what I have written here is just the equation for dn, that is the number of modes in momentum p, as a function of k, as a function of mu, right? And a couple of variations here and there, that's all. One more last thing we have to consider in this derivation is, for any electromagnetic wave, there are two independent modes inherently. So this involves the concept of polarization. So you can always represent an electromagnetic wave in 3 dimensions with a polarization along the electric field and along the magnetic field. So because of the nature of light waves, there are two independent states associated with each lattice point. You have L, M and N, and the final result is the number of modes of oscillation in the frequency interval mu and mu plus d mu. So dn can be represented as, if I take this equation, 8 pi mu squared by c cubed d mu. Thus per unit volume, that is dn by v, or if I write v here, per unit volume, the number of states or modes is 8 pi mu squared by c cubed d mu. Now this is a very important equation. The number of modes per unit volume is given by the following equation. This is a very important equation, and this concludes our part 3. Now let's do part 4, which we are almost close. Like we're done with 80% of the job. Now we have introduced that we have waves in a box where there is no loss of energy. But one more thing we have not considered is temperature. We will now introduce the idea that waves are in thermodynamic equilibrium at some temperature T. Right? Now, from the theory of equipartition of energy, we know that in thermal equilibrium, we evolved half kBT of energy, where kB is the Boltzmann constant, to each degree of freedom. That is because if we wait long enough, there are processes which enable energy to be exchanged between the independent modes of oscillation. Thus, if you wait long enough, each mode of oscillation will attain the same average energy E bar, right? So I can write E bar, and now we know that average energy E bar of a system can be represented as KT. I've already done that in the previous video. I'll also put up a link where I do this derivation, right? So, and when we treat the whole thing, we're treating them as harmonic oscillators, right? And the average energy of a harmonic oscillator is given by kBT. Now, what we want is the energy density. We are looking for the energy density, that is energy per unit volume, right? Now, the energy density per unit volume per unit frequency. Let's consider that. That is dE by d mu equals du into d mu. Or let me write this way. U as a function of mu into U as a function of mu. This is the number of modes in volume d mu in volume V. That is 8 pi mu squared by c cubed into the average energy of each mode, right? So the energy density, how do I say this? The energy density of radiation per unit frequency interval per unit volume is given by this. where E bar is kT, right? So I can just write the equation that E of mu is equal to 8 pi mu squared by C cubed E bar. Now we already know that E is equal to kT, so I can just write that this is equal to 8 pi mu squared kT by C cubed. Now this is the result we think is not nice. That is, we don't want this result. And what does that mean? That means mu, which is the energy density per unit frequency, is equal to 8 pi mu squared kT by C cubed. The energy density of radiation per unit volume. Now what does it say? It's a function of frequency, right? Yes. Now this is what was called the Rayleigh-Jeans Law. The Rayleigh-Jeans Law. Originally derived and proposed by Lord Rayleigh in the year 1900. And this result was very bad news. The energy density, you can see that mu, if I plot this function, now 8 pi C cubed k T are all constants. We're considering at one temperature, right? If I plot mu as a function of mu, it's an x squared function where you see that the energy density of radiation diverges at high frequency, just blows away. And Einstein, in fact, expressed this result rather forcibly. So you know what he did? He just did this integral. So you find the integral of this function for all values of frequencies, and just said that this goes to infinity, so this is wrong. And this famous result, this famous mistake, that's called a catastrophe, was called the ultraviolet catastrophe. Which meant that the total energy of a black body ultimately diverges at very high frequencies. And although it one fact we need to know is, although it diverges at high frequency of UV light, it is actually in excellent agreement when you see the results with, at low frequencies and high temperatures. That's it for this video. We have derived the ultraviolet catastrophe, how we got the Rayleigh-Jeans Law. We've done a 4-part derivation. If you have any doubts in this derivation, do comment in the video. Do let me know. In the next video, we'll see how Max Planck, a German physicist, came forward and tried to find a solution, thereby inventing a new subject. That's it for this video, guys. Thank you.